Hello and welcome back to part 3 of our M1 lesson. We're going to be looking at how we can represent these rates graphically. So what a rate looks like. Right? If we remember that a rate is a comparison of two things, that's exactly what a graph is doing, right? Our x-axis is representing one variable. In this case that we have here, we can see that our x-axis is talking about time. And our y-axis is going to represent something else. In this case, it's representing distance. So when we're comparing these two things, when I'm comparing distance to time, and just like in the past, we're comparing y over x, right? This is really going to tell us about speed. How much distance can I cover over a certain amount of time? That's represented by speed. So let's break this into a few parts. So starting off, we have this flat section. Let's call this section 1. Right, and we're going to analyze this. It looks like that 20 seconds has passed and we haven't moved. Right, so section 1, nothing's happening. Right, maybe you're sitting on the couch. Move on to the next section. Right, and I'm going to break these into linear sections, right, where it's represented by a straight line, because those have different relations of distance and time, right? It's constant speed, right? Constant change between those two variables, only for those straight sections. So section 2. Now it looks like after 20 more seconds, right? We jump from 20 to 40. We cover a distance of 2 meters, so not crazy far. Maybe this is where you get up from the couch and you walk to your kitchen. All right, you take a few steps, you get to your kitchen. Next step, right? Now it's 20 more seconds, but this time we only gain 0.5 more meters, right? So notice that we see less steepness in the line. We're moving at a slower pace, right? The same amount of time passes, but I don't go quite as far, right? So maybe this is you got to your kitchen, you're taking a bit of a break, you look around, and then you walk over to the fridge, right? You haven't gone very far. We have another section here where it's flat, right? So 10 more seconds passes, but we don't move at all. So section number 4, you're standing there stationary. Maybe you're picking a snack, right? No movement. Doesn't take that long. Moving on to the next section. Let's call this section 5. So notice now we have a negative change, right? We're actually going down. Our distance is decreasing. So in a lot of cases, we can think of that as traveling backwards, right? Maybe you've walked back, not all the way to where you started, right? You're not going back to the couch because that would be at a distance of 0. So maybe you walk to the table, right? To your kitchen table. It's halfway from your couch back to the fridge where you're at. And then the last step, right? Stationary again. Maybe you're eating, right? So things to think about when you're trying to understand a scenario, right? What are your two units? In this case, it was distance and time. What are the units that those are using, right? This one was meters and seconds. You wouldn't really want to say this was the traveling of a car, because if a car took 20 seconds to only go 2 meters, right, there's something wrong with that car. And then keeping track of, right, are my values increasing? Are they decreasing? What could that mean, right? Do I have that flat point? Do I have an increasing, a decreasing? And if we remember all of these values, right, the comparison of those two variables, this was a representation of the idea of slope, right? It's the comparison of y to x, right? If we remember slope, what it really is it's a rate of change, right? It's talking about the change in y divided by the change in x, right? Or some way we saw that was m equals, we can call it the rise over the run, right? Or we could talk about it as a comparison of 2 points, right? My furthest y value, subtract where I started, right? Where did I end minus where I started? That tells me how far I've traveled. And then the same thing with x's. Where did I end? Subtract where I started. That tells me the difference. So when we're talking about the rates graphically, we're just talking about the slopes. So let's look at a couple of examples here. We have a couple of situations. First one here, the following graph represents the temperature of an oven as it heats up. How fast does it heat up, right? How many degrees, if we're looking at our units, how many degrees Fahrenheit, right, change in Y per minute, change in X, right? What is the speed that it heats up at? So again, we're going to find the slope. For a lot of these, we're going to be using that formula there that says m, right? M is our slope variable. y2 minus y1 over x2 minus x1. Right? So when I'm looking at these points, I'm going to call my first point point 1, which means that these coordinates are x1 and y1. And if I call this latter point, right, we read graphs left to right, just like we read books. If I call this latter point point 2, then this becomes my x2 and my y2. So I take y2 first. I take my last y value, 450 degrees, right? That's the temperature that my oven ends at. And I subtract where it started. It started at 50 degrees, right? Your house is not 0 degrees Fahrenheit, I hope. And then in terms of time, right, my denominator is going to be my comparison of x's. Again, going back to that second point, 10 minutes later, subtract the 0 minutes from where I started. Right? When I do 450 minus 50, I get 400. Again, let's add some units. That was degrees Fahrenheit. 10, that was minutes. Right? So this tells us it took 10 minutes to heat up 400 degrees. If we want to talk about that rate, let's talk about it as a unit rate. Let's say per minute, right? 400 divided by 10. Every minute that passed, my temperature went up 40 degrees Fahrenheit. So that's our rate, right? That's our speed that this oven heats up at. So 40 degrees Fahrenheit per minute. And we see, right, that's an increase. It's a constant. We see that straight line, right? So we can say that it's a constant rate of 40 degrees Fahrenheit per minute. It didn't heat up 30 degrees in the first minute and then 70 in the second minute and then 45 in the third minute, right? It's a constant straight line. So looking at example 7, the following graph describes the amount of fuel a truck has during a trip. What is the truck's fuel efficiency, liters per kilometer, or we can even turn that to liters per 100 kilometers. So let's look at this one. Again, using that same formula, label my points. I'll call this x1, y1, and x2, y2. So point 1 is where we start, right? After 20 kilometers in your trip, you have 50 liters of fuel. And then later on, after 120 kilometers in your trip, you're down to 40 liters of fuel. So it looks like 40 minus 50 for my y values, right? Which makes sense because this time our fuel is decreasing. We do have a negative slope here. We want to make sure we include that, right? The positive, the sign of our slope tells us some context. So don't worry if your values are negative. 120 minus 20 on the bottom, right? Again, these are telling us the change in x and y. So in terms of y, right, that means my fuel went down by 10 liters. And then for x, that means my kilometers went up by 100 kilometers. So here we would say, right, I lost 10 liters for every 100 kilometers I drove. Or if I reduce that to a unit rate, which this is the common rate that we measure fuel consumption. But if I want to convert that to a rate I'm more from a unit rate to deal with, that'd be 0.1 liters for every kilometer I drove, right? And we're calling it negative because that's the amount I'm consuming. I have less fuel for every kilometer, right? I wish that the further I drove, I gained more gas in my gas tank, but that's not how it works. So there's a couple of questions for you to try down here at the bottom. Give those a try. Again, if you're stuck on any of these practice questions, feel free to check out the practice video for some in-depth solutions. But take a minute, pause, and I'll put the answers up here for you. All right, so if we look at that first scenario, right, your scenario could very well be different, but here's what I came up with. So for the first segment, right, again, going only for those linear chunks, it could be you walking to the store, right, takes you about 30 minutes to go 2 kilometers. Second segment, you're stopped, so maybe you bought a Slurpee, right, you bought a drink. Third segment, maybe you walk to the park, right, you're still getting further away from where you started. And then the fourth section, I said you got to ride home, right? Because you travel all the way back home in a much quicker amount of time than you're walking, right? You're a very fast speed. So unless you decided to run or ride a bike, right, it has to be something that gets you there quicker, right, than the first, second, and third sections. And the last example, so the graph to the left shows an all-terrain vehicle traveling over time. Over which interval is the ATV traveling the slowest? That's going to be number 2 because we have the least steep slope. And when is it traveling the fastest? Interval 5, even though it's going backwards, it still has the steepest slope. When does it start to return to its starting position and when does it get there? Well, that's going to be that section 5, so it looks like right around between about 28 to 32 seconds, right? And then what does a zero slope mean in the context of this graph? It means that we've stopped, right? Someone's hit the brakes, we aren't moving, but time is still passing, right? So it looks like from about 20 seconds to 28 seconds, there's no change in distance, right? So that's a full stop. All right, so that brings us to the end of M1, right? The rates measurement unit in Math 20-2. If you have any questions, leave them down below or send me an email. And if you want to see these try questions in more thorough, detailed solutions, keep a lookout for that video.